we've got our 3 rules. First rule, concrete's made out of cement and aggregates. Stress equals force over area, and that steel has a strength of about or over 300 megapascals. Right? There are 3 rules. We're going to look at rule number 2. Rule number 2 is that stress equals force over area except for bending. Does anyone remember what the formula for bending is? My over I. My over I. Right? Now, in order to know my over I, the first thing we need to do is we need to know what the M stands for. Can anyone remember what M stands for?
Modules.
M is the maximum bending moment, right? Well, we'll go with the bending, it's actually the bending moment. But I like to use M star, which is factored up bending moment. Or what you can write is M max is what we usually want to find, right? Now, the other 2 values, Y and I, they're going to be, Y we're going to find, and I is usually going to be given to us. So, can anyone remember what I stands for? Okay, I think of it as moment of inertia, but as I learned, through some lecturer saying to me, well, actually, it's second moment of area, right? There's a slight difference in those 2 things. Effectively, for you, it doesn't matter. I like moment of inertia because it starts with an I, but I'm going to write the correct one up here, at least today, which is second moment of area. Now, area is measured in what?
Meters squared.
We measure area in millimeters squared, don't we?
Yeah.
Usually, right? And that way we can have our song. Can we get our song, guys? We go, come on, we're recording this, we've got to do this. We go together like megapascals and millimeters squared. Oh, look at those. That's the worst one we've ever done. Okay, guys.
I thought that was our best.
Now, if we're taking the first moment, it would go from millimeters squared to millimeters cubed. Because we're doing the second moment, it goes from millimeters squared to millimeters cubed. Because it's the second moment, we go from cubed to millimeters to the power of 4. Now, song still works, right? If we use the values in millimeters to the power of 4, we're going to have our answer be in megapascals. And that's good because megapascals are what we usually use. Hope I'm not keeping you up. Okay. Now, Y bar, we wrote Y in this subject. Oh, technically we like to use IXX, right? And you might see that around sometimes. That's because for every shape it has 2 moments of area depending on if it's standing up or lying down. We know which one's stronger. If we have a piece of steel, a piece of timber or steel that's, if we have a rectangle, do we want it? Is it stronger?
D is good.
Big D is good. So we want to have the bigger depth. Here we'd have a small depth. Now I'm not going to go into the formula for that. I will actually use calculations that I've done previously, which we did when we did this experiment. But the IXX value will be given to you, right? Now, one thing I will show quickly while I've got, for steel sections, this book here is what young engineers go out and buy, right? And then what that's got is it's got the IXX values for all the steel shapes that you're likely to use, right? If I open the book to here, it's this column. This column lists the IXX values for all of those steel sections. Okay. For concrete, it's a bit tougher. Concrete, we do something a bit different. Okay. Now we need to talk about. We need to talk about Y bar. Now we wrote Y here. We wrote Y at uni. You'll use Y bar, right? And Y is the distance from the neutral axis to the extreme fiber, right? Extreme fiber sounds like something that your grandparents might have for cereal, like their breakfast. But especially if they were like once cliff jumpers or something like that. Extreme fiber for people who really need it. Keep things moving. Okay. Thank you, Darcy, for laughing at that. Okay. So I'm going to explain what that means, right? The distance to the extreme fiber. If I have a section that's bending, right? This is my thing that's bending. This part here, is it being squashed or is it being stretched? Does it look like it's being squashed or stretched? Okay, so it's in compression. Is this part being stretched or? Yeah, okay. So I helped you out there, right? Compression and tension. This part here in the middle, it's neither up nor down, yeah? Right? What's that? Compression or tension? Nothing. It's one of those annoying neutrals, right? There's this bit from Futurama, the neutrals. It's when they think they're going to die, they say, "Tell my wife hello," right? Because they they don't feel positive about anything. They're neutral about everything, and it has exactly an equal number of amount of likes to dislikes, so that whenever it goes up, the next person who views it always makes sure to unlike it, so that it has exactly perfect 50-50 likes to dislikes. Anyway, so the neutrals, right? That's the center of this beam. Now, in some cases, a little bit more complicated cases, we're going to talk about things like T-shaped beams. T-shaped beams, the neutral axis can be a little bit higher. But for the moment, we're just going to learn about the situation where the neutral axis is right in the middle. Now, where's extreme compression? At the very top. The atoms, right, or the timber cells at the very outermost layer, they're in extreme compression. What about down the bottom here? Extreme tension, right? It's required that you say extreme every time you do it. Now, in this case here, if I have this rectangle, right, and I say that's the neutral axis, right, this here is the extreme compression, and that's extreme tension. The distance from the neutral axis to the extreme fiber is what? Half the d. Yeah? If this is the depth, well, here's what I'm going to do. If that's y, and that's d. Does that make sense? It's not always half d. I don't want to bog you down too much here, but if we have a T shape, the neutral axis will be closer to the top, and in that case, we'll have two y values, right? This will be yc, and this will be yt. Does that make sense? Because we've got two different extreme fibers. Yeah, we've got the extreme compression and extreme tension, and this is the distance from the neutral axis. We all okay with that? Yep. Okay. We're using rectangular shapes, right? We're using rectangular shapes. So what we can do is, if we're using these values here, I think I can go... These are the values of the ones that we tested. We had a 20 gram piece of balsa. It was 26 millimeters depth, right? 26 millimeters in depth. And all of them were 6.5 breadth. So what is the y value then? What would we guess the y value is?
13.
Y equals 13. Now, what we need to know now is we need to know how to find... We said this is going to be given. Y for a rectangle is half d, right? For rectangles. For a rectangle equals d on 2. Yeah? We need to be able to figure out the m. Now, how do we figure out the m? Well, again, I'm going to use the easiest possible example. The easiest possible example is if we have a centrally loaded beam. Hey, and that's what we tested, wasn't it? OMG, that was exactly what we tested. Yeah? Okay. So, what we're going to do is we're going to call this is a load at a single point. So the convention is to call this P. Yeah? P is a single point. How wide was our beam?
350.
Okay. 350 is what we used for our more recent examples, right? That's in millimeters. Okay. And then we're going to call that L. Now, I'm going to give you a little bit of a tip, which won't work for everything, but it will work for simply loaded beams. If we want to find the maximum value of M, right? our M max or M star, if we want to find that value, we can use a formula which says M max for a simple beam, right? M max for a simple beam is equal to PL on 4. Okay. What is our P in this case? What is our P?
110 newtons.
Okay, so what's our L?
350.
350. Multiply those and divide them by 4. What do we got? Okay, now that's in Newton millimeters. Yeah?
Yeah.
Okay, so I'm just going to write that in here. So our Y bar and our M max. Will, can you remind me what was my Y bar for this? That was my D. What was my Y bar? My Y value. Okay, it was 26 millimeters deep. Right, that's the neutral axis. 26 millimeters from top to bottom. How far is it from the neutral axis to the extreme fiber? Good work. Okay, I was worried for a second. Could you give me that value again? 9,600. Okay, great. Now, what we need is a third column, which gives me the IXX value. Now, when we did this last time, I had already calculated these, so I'm going to look at my... I'm going to save you that because I don't want to confuse you. I'm just going to look up here where I've already worked out the IXX value. So the IXX value for this one is conveniently 9520. I will solve the other ones for you. 5, 7, 6, 8, and 230. I've already worked out those IXX values. I've already calculated those values. I'm just going to write down what the units are for this just below. That's in millimeters, that's in Newton millimeters, and that's in millimeters to the power of 4. So because of all our units are in millimeters squared or millimeters something, right, we can get our answer will be in megapascals. So I'm going to rub this out now. I'm going to rub out this board. We've already calculated our PL on 4. We've already got our value. So what we can do now is we can use this new formula. Sigma B is equal to my over I. Oh my. Okay, so our value here is 9625 times, what's our Y?
13.
What was our Y? Good job. Okay, divided by, what was our IX value?
9,520.
And 20. Now, guys, close enough. What do you think our answer is going to be? Just roughly. This is where using that estimation skill is really valuable. Without me even getting the calculator out, what do you think the value is going to be?
13.
About 13. Does anyone want to type it in the calculator?
That's 13.14.
13.14. What's our value? Megapascals. Yep, that's exactly right. Thank you very much, mate. Okay. Now, okay, what we're going to do is we're going to try and do the next one. Okay, we've done one example, right? That's the deep beam. Let's try the next one. Okay, the next one, we had 15 grams. It was 22 millimeters. Will, this is you. This is your moment to shine. What's the Y value? 10 points to Gryffindor. Okay, what's our M max? Can someone figure that out for me? It's 80. 80 times 350 divided by 4. What's that going to be?
7,000.
Sounds about right. That was what I had in my head. Okay, so let's type it into the calculator. Ready? So sigma B equals my over I. We've got 7,000 times 11 divided by... Guys, just 1 second. What's our value?
5,768.
Can you give me that value?
13.8.
13.35. Hey, they're the same. That's good because they came from the same tree. Yeah, the balsa, it's the same value. They're both 13 megapascals in bending. Okay, your homework, I'll take the photo of this, is to calculate the last one, and we're going to talk about that tomorrow. We good?
Yeah.
Good job.